Alright, let's dive into the fascinating world of natural hydrogen, sometimes called white or gold hydrogen. Forget the hydrogen you hear about that's made in factories using fossil fuels or electricity. This stuff is generated deep within the Earth through natural geological processes, and it's generating a lot of excitement in the clean energy world. Think of it as Earth's own hidden, carbon-free fuel source. Why all the fuss? Because exploring for and developing natural hydrogen could provide large quantities of low-carbon hydrogen, potentially at a price point similar to or even cheaper than hydrogen made from hydrocarbons. The current hydrogen industry largely relies on hydrocarbons, which isn't exactly a clean process unless coupled with carbon capture and storage, which isn't widespread yet. Even green hydrogen from renewables-powered electrolysis makes up only a tiny fraction of global output. So, finding naturally occurring hydrogen accumulations is seen as a promising path towards a sustainable energy future. But how is this natural hydrogen created? It's not magic, it's geology. There are a few main ways the Earth whips it up. One key process is called serpentinization. This happens when water reacts with iron-rich minerals found in certain rocks, particularly mafic and ultramafic rocks, deep within the Earth's crust and mantle. When iron oxidizes, it releases hydrogen. This often occurs in places like rift zones, ophiolites, and Precambrian continental lithosphere. Another significant process is radiolysis. This involves radioactive elements like potassium K, thorium, and uranium U naturally decaying in minerals. This decay emits radiation alpha, beta, and gamma rays which can break the bonds in water molecules, splitting HO into hydrogen H and oxygen, along with other reactive species. Radiolysis is a known source of hydrogen in deep crustal fracture fluids and certain geological environments. Other abiogenic non-biological sources include mechanoradical reactions on wet fault surfaces, where mechanical forces break CO bonds in silicate minerals, also generating hydrogen. Hydrothermal alteration and the reduction of water during iron oxidation in minerals can also produce hydrogen. Additionally, some primordial hydrogen might still be stored deep within the Earth's core and mantle and degas to the surface. Magmatic hydrogen emission has also been observed during or after volcanic eruptions, linked to the oxidation of hydrogen sulfide. Natural hydrogen can also have a biogenic source. This involves biological processes, including both thermogenic heat-driven and microbial processes. Microorganisms in the soil can produce hydrogen through various mediated processes, which is important to consider when looking for geological sources. Once generated, this hydrogen gas needs to get from its deep source to a place where we can find it. Like oil and gas, it migrates through the subsurface. This migration can lead to surface hydrogen seepages. These seeps are essentially hydrogen slowly leaking from the ground, acting as a primary indicator of a potential underlying resource. Think of them as tiny, natural hydrogen leaks that geologists are trying to sniff out. One fascinating surface manifestation linked to hydrogen seeps is the presence of subcircular depressions SCDs, also known by various local names like Zapatini, Carolina Bays, or fairy circles. These rounded topographic features have been observed in several locations globally and have been attributed by some to localized collapse caused by the alteration of rock along vertical hydrogen migration pathways. While a correlation has been found in some places, scientists are still gathering data to confirm a direct cause and effect relationship, as not all such features might be related to hydrogen leaks. Still, finding these can be a clue. Hydrogen seepages have also been reported near outcropping fault zones. These are fractures or discontinuities in the Earth's crust where rocks have moved past each other. Faults can act as pathways, allowing hydrogen generated at depth to migrate upwards towards the surface. Exploring near faults is another strategy in the natural hydrogen hunt. The search for natural hydrogen is still in its early stages, but it is gaining momentum rapidly since the discovery of a large accumulation in Mali and initial production there. Scientists and companies are now adopting exploration approaches to identify where hydrogen might be generated and where it might accumulate. It's like a new kind of treasure hunt, but instead of gold nuggets, they're looking for invisible gas. Exploration often starts with a top-down approach, focusing on identifying those surface seepages. Soil gas sampling is a common and cost-effective method for early exploration. This involves measuring hydrogen concentration in the soil, often coupled with sampling the gas for composition analysis to help understand its origin. Handheld drills or probes are used for this. To make these surveys more efficient, researchers are developing conceptual designs based on where hydrogen is more likely to be found, such as around those SCDs or near fault zones. For SCDs, the outermost ring seems to have a higher probability of high hydrogen concentrations. Near faults, transects perpendicular to the fault are useful. However, interpreting soil gas measurements isn't always straightforward. One challenge is the presence of anthropogenic hydrogen, which is hydrogen generated artificially. This can come from things like the corrosion of steel casings in wells, corrosion reactions from groundwater or drilling fluids, decomposition of borehole water reacting with sediment and drilling tools, or even heat from drill bits causing organic matter to crack. Careful analysis, including mineralogical and isotopic studies, is needed to distinguish natural hydrogen from these drilling-induced or human-related artifacts. Another complexity is that hydrogen appears to be ubiquitous in soil and can be produced by multiple microbial processes, sometimes with concentrations and signatures that overlap with geological sources. Distinguishing between microbial and deep geological hydrogen requires support from geochemical data and analyzing associated gases like carbon dioxide, methane, nitrogen, and helium. To locate potential hydrogen sources and accumulations at depth, geologists are using techniques similar to those used in hydrocarbon exploration, but adapted for hydrogen. They are studying the geological ingredients required for a natural hydrogen system, a source rock that generates hydrogen, porous reservoirs where the hydrogen can accumulate, and impermeable seals that trap the hydrogen, preventing it from leaking away. Identifying regions with all these components is key to finding commercial deposits. Various geophysical methods play a crucial role in understanding the subsurface and identifying these ingredients. Techniques like aeromagnetic gravity, radiometric, and resistivity surveys can help characterize source rocks, particularly mafic and ultramafic rocks, which are often rich in iron and can generate hydrogen through serpentinization. Magnetotelluric surveys and seismic surveys can help delineate subsurface structures, identify potential reservoirs, and map fault zones that might act as migration pathways. Integrating these different geophysical datasets provides a more comprehensive picture of the subsurface. While seismic is widely used in hydrocarbon exploration, its direct application for hydrogen might cause issues, potentially missing hydrogen reservoirs depending on how sharp the boundary is between the reservoir and the sealing rock. Delineating source rocks using electromagnetic, gravity, and magnetic data, and then looking for reservoirs nearby, is a strategy to mitigate this risk. Beyond traditional methods, advanced tools are being employed. Satellite imagery and remote sensing are used to identify surface features like SCDs and fault zones that might indicate underlying seeps. Researchers are also looking into using artificial intelligence AI and machine learning ML to process and interpret the large datasets generated by geophysical surveys and other exploration activities, aiming for more efficient decision-making in identifying prospective areas. Natural hydrogen exploration is happening in various parts of the world. In Australia, areas like the Perth Basin and the Yilgarn Craton are being investigated, with studies focusing on soil gas measurements around SCDs and fault zones. South Australia, in particular, has seen a gold rush of sorts, with multiple companies applying for exploration licenses covering a significant portion of the state, driven by drill hole shows and possible fairy circles. Canada is another area of interest, with companies like Go Metals specifically forming subsidiaries to explore for natural hydrogen in places like the Canadian Shield. The United States Geological Survey has even developed prospectivity maps for the contiguous United States, identifying areas like the Mid-Continent region and the Central California coast as having high potential and suggesting previously unrecognized areas like the offshore eastern seaboard might be prospective due to long-distance migration. The exploration workflow typically involves several steps: screening existing data, geological reports, maps, geophysical surveys, historical records using satellite imagery to spot potential seeps, identifying prospective source rocks and seals, analyzing existing gas samples, conducting fieldwork including soil gas measurements and potentially 24/7 monitoring of seeps, running geophysical surveys, and potentially drilling exploration wells using specialized hydrogen detection equipment. Understanding environmental factors and engaging with stakeholders are also part of the process. Despite the growing interest, the understanding of hydrogen in the subsurface remains partial and fragmented. Locating and characterizing commercial accumulations of natural hydrogen requires more research and exploration. The relationship between hydrogen concentration and geological features like faults and depressions can be complex, influenced by factors like rock type, deformation, and rheology. However, the potential for natural hydrogen to become a significant low-carbon primary energy resource is a powerful motivator. Identifying natural seeps is considered a critical step in validating a hydrogen system and understanding migration processes. Developing a statistical understanding of hydrogen distribution around surface features like SCDs and faults can help guide soil gas surveys and target areas with a higher likelihood of detection, making exploration more efficient. In summary, natural hydrogen is a potentially game-changing clean energy source generated within the Earth. Its formation is linked to processes like serpentinization and radiolysis. Geologists are actively searching for it by looking for surface clues like circular depressions and fault-related seeps, and by using a suite of geophysical and geochemical techniques to map the subsurface hydrogen system, the source rock's migration pathways, reservoirs, and seals. While challenges exist in distinguishing natural hydrogen from other sources and fully understanding its subsurface behavior, ongoing exploration efforts in places like Australia, Canada, and the US are pushing the boundaries of this new frontier, aiming to unlock Earth's hidden clean energy treasure. It's an exciting time for geological exploration, where sniffing out the right kind of gas could help power the future.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.